Good afternoon. First, I'd like to thank the organizer for giving me the chance to talk today. And I realize that the topic of my talk is very different from this conference, so please do bear with me. So I want to talk about this work as was done. It's not a new work. It was done in about 5 years ago. And during that time, I want to do something interesting. So, well, I'm from Bioinformatics Institute. I do bioinformatics. I want to do something interesting in physics. So, some review. So, I read up some paper concerning time machines. Some people talk about closed time-like curve, some using some quantum phenomena. Even in psychology, this guy sent me an email that he claimed something, sent me his paper. So there are also a number of papers that saying that it's impossible to build a time machine. These are some of the papers. And the reason why, one of the main reasons why people argue that it's impossible to build a time machine is they formulate some thought experiment that with thought experiment, they have some logical arguments against building a time machine. One of the thought experiment, there are several versions of this kind of thought experiment. One of these is auto-infanticide, or what they call it grandfather paradox. Suppose in 2011, for example, I go into a time machine, and I get out in 20 years earlier, 1991, from time machine. So I really could meet my younger self 20 years earlier, right? If I'm an adult, I can meet my younger self as a little kid. Then if time travel is possible, if I can do this, then I should, in principle, be able to kill my younger self. Sorry, kid, kill my younger self. But this leads to a paradox, because if I kill my younger self, there's no younger self, then there's no me in 2011. If there's no me, I cannot travel back in time to kill myself. So this is a paradox. So you will say, okay, you can't resolve this paradox. That means you can't build a time travel, right? Time machine, right? So there are also other paradoxes. So Novikov, actually Feynman and Wheeler, a long time ago, they talked about self-consistent principle, and Novikov published a paper about self-consistent principle, right? So what they say is, perhaps you still can resolve the paradox, just that you have to impose some self-consistency. If you travel back in time, so this is time past, future. If this is me, alive, if I'm alive here, I have to be alive in the past, right? Alive all the way, travel in time, and perhaps I cannot kill myself. Then this is self-consistent. This does not go against the idea of the possibility of time travel, okay? So they say that the past can be changed in a self-consistent way. Okay. So some more schematic. So this is what I show you. There's one schematic I thought of is possible. Well, if you can be dead and then you can be resurrected, then this loop is self-consistent. Of course, we know from here to here is impossible. Okay, this is just a self-consistent picture. So then I'm thinking, what other physics is the self-consistent principle consistent with? And I set up to work out some mathematical framework, hopefully to frame this self-consistent idea into some mathematical framework. I found that if I use, I model a universe with Markov chain as a Markov process, and the self-consistent principle comes out naturally if I model a world with a Markov process. So it's just a simple model. Okay, this time I want to tell you what our contribution is. I'm not here to prove that time travel is possible. I'm not here to discuss how to make a time machine. I want to support the self-consistent principle by the use of just some basic axioms of probability. Okay, basics are axioms of probability like normalization. You cannot have negative probability. This kind of axioms. Okay, now I want to describe how I model the universe with the Markov chain. So there's no time travel in this slide, just simple model. The universe consists of several states. Here I just draw 3 states. There can be many states in the universe. For each, and then we discretize the time. And suppose we are at state B at time 1, then we have a transition probability of going from B to A, B to B, B to C at time 2, like this, with some probability. And this probability must be normalized. And we can go on tracing our path in the universe. We could go in the red path, or there's just many realization. Okay. So mathematically, we say that we go from one state to another state, go on like this, and then this is the probability of getting a path pi m. Suppose pi m is this red thing, then this is the probability of getting this path. Okay. Then if we sum over all possible paths, of course, sum over all probability of all possible paths is 1, right? So then I invent the kind of loop. Okay. So you can see from this, the condition, our state is always conditioned on the past. State 2 condition on state 1, state 3 condition on state 2. We always condition on the past, only one step in the past. This is called the Markov chain property. But what if we condition on the future? That means the future state affects the past state. We condition on the future, one single loop. All these are conditioned on the past, as the same as Markov chain. But then there's one time where we condition on the future. That means we model a world as some signal traveling from the future to the present to affect the present. So I can write down this kind of probability of getting a path, and then this kind of probability axioms, which is very basic, normalization, so on and so forth. And then this is just short form. I write this symbol as a condition from k minus 1 to I plus 1. I is here, k is here, okay? And then I want to impose probability of all possible happening in the universe is 1. Then from this equation, 1, 2, 3, 4, 5, I can derive this equation, okay? So I can't derive this equation in this talk, but you can look at my paper, okay? So that's this equation, okay? So if sigma takes value of 0 and 1, 0 means dead, 1 means alive, then this is sum over 4 terms, right? 0, 1, 0, 1. So I write out 4 terms, simplify, factorize, I get this, okay? Then what's this? We talk about auto-infanticide. 0 means dead state, 1 means alive state. And then we want to impose that if you are dead in the future, you can't be you can dead. If you are dead in the past, you can't be alive now. No restoration, right? So this term is gone. This term is 0. Then what is this term? This term is either 0 or more than 0. Okay, if it's 0, that means you are dead at time in the future. You are dead in the future, you can't travel back to kill yourself. If this more than 0, strictly more than 0, there's only 2 possibilities. Equals 0 or strictly more than 0. If this strictly more than 0, this term is gone. This more than 0, that means this whole thing is 0. That means this is 0. This 0, what does it mean? You look at the physics of this. This is a probability that you are dead now, conditioned on whether you are dead or alive in one time step before and whether you are dead or alive in the future. This is a probability that you are dead now, condition on one time step before and condition on whether you're dead or alive in the future. This you are dead in the future, this you are alive in the future. These two probabilities are the same. They are the same, that means the future cannot affect whether you're dead or alive in the next time step. That means different ways you can interpret this. You cannot travel back in time, or you can interpret as you travel back in time, but it cannot affect the probability of whether you are dead or alive now. That means you can't kill yourself, okay? unchanged bus. Okay. So this another here. I go through this really quickly. Is another paradox which I also use such argument to prove. I won't have time to go into details. All these derivation, some condition, prove them don't get lost. You can read this paper for some detail, right? So this is a probability of recording the proof is 0. Yeah. So okay, I want to end my talk. So we have auto-infanticide in the Deutsch unproven theorem paradox. I have not described this very much due to time limit. Okay, can be percolated in the time travel. There's some confusion if the confusion about auto-infanticide. This kind of paradox can be resolved, can be made self-consistent if restoration is possible. I talked about this before. And this paradox can be also made self-consistent if you have some proof and then you lost a proof and then you can derive the proof. Okay, thanks. Yeah.
Allow you to go back in the past?
Actually, I'm not so familiar with that. So,
yeah. Wormhole and then you go.
Yeah. Yes. Yes, quite complicated. Yes. These few papers. Sorry, these few people, they talk about closed timeline curve and they talk about possibility of making closed timeline curve. And there are some papers say that closed timeline curve cannot be stable. There are some papers claim that they can be stable. But I'm not so familiar with this field. Inner equation. Yeah. Thanks.